This morning, it occurred to me that our title could apply to most every paper on the program, so not very descriptive. So maybe the takeaway is learning without a projection facility. And I'm sure when you woke up this morning, you didn't expect to spend the whole morning thinking about projection facilities. Okay, so this is what we do. We think of rational expectations as a strong assumption. We want to take a step away from that, but we want some discipline on the step. So the idea is to have a forecasting equation. Theory kind of dictates a bit what that forecasting equation might look like. And then we have some updating rule about the coefficients, and we can discipline that with thinking about the econometric problem that the agents are facing. The algorithms we usually look at are variations on recursive least squares, sort of depending on how the data is averaged, so a decreasing gain or a constant gain. And so the constant gain is kind of going to be the target of my talk here today. So that's what we think, and then in our papers, that's usually what we write. We think we're done, and we feel like we're on pretty good footing. But anyone who's worked with constant gain learning really knows it doesn't end there. Okay. So this is what a typical fall office hour looks like at an unnamed Southern California university halfway between Los Angeles and San Diego. A student's very interested in applying constant gain learning to some topic. That makes the professor very happy. They pin down their model, and then off they go to try and let's just simulate, see what happens. And then they disappear, and the student comes back several months later, a little bit distraught, and says, I don't know what's wrong. I keep going through it. I can't find an error in what I've done, but sometimes my simulations explode. And the professor says, oh, well, did you use a projection facility? And the student says, what? And the professor explains very patiently, well, sometimes your algorithm might just sort of pop out of the basin of attraction, and you just want to project it back in. And the student wants to know, well, how would I go about doing that? And the helpful professor says, well, there's a bit of an art to it. And then the student says, okay, I'm going to go deep money instead. So we have this, I sometimes call it the dirty little secret of the literature. Sometimes the trajectories escape this basin of attraction. As George was saying in his discussion, sometimes you want that, but a lot of times you don't. And so there's various factors that can affect that. And the size of the gains in the algorithm has a lot to do with the likelihood of escaping this base of attraction. You can have large shocks, or as Tom would call it, the most likely unlikely sequence of shocks can push you out of a base of attraction. And so while everything was nicely disciplined on my first slide, and the second slide, well, you need to start thinking about it. So the projection facility really needs to do two things. It needs to arrest the explosion, so it stops updating, and then it needs to project the coefficients back into the region of stability. And so the point I'm going to pick on a little bit in the talk is all of that's kind of predetermined by the researcher. So it's chosen. It's a little harder to think about how to discipline that. So depending on the question, whether you're worried about a projection facility or not matters. So if your question really is about the stability of an equilibrium, so thinking about a probability 1 convergence, like you would have with recursive least squares, well, as the gain is decreasing over time, the likelihood of hitting that projection facility is diminishing as well. And so the projection facility is not such a big deal in questions like that. If you're working with a constant gain learning model, best case is you're hoping that you're converging to a distribution around the equilibrium. But because of this constant gain, this time invariance of the way you're weighting the data, there's always this possibility of hitting the projection facility. And then if the larger the gain you have, the more likely that's the case. And then what's really happening most often in these models is that there's a lag in the model of the forecasting equation, and you hit an explosive root. And so if you have lags in your model or in your forecasting equation, it kind of makes the the likelihood that you hit the projection facility more possible. So just to kind of see how often this can happen, this is just a motivating example. So just thinking of a linear univariate model, it depends on forward expectations one period, it depends on a lag, the endogenous state variable, and then a white noise shock. The MSV solution, of course, is just a simple AR1 model with a value for A that's going to be inside the unit circle. And so the idea is that we just give them this perceived law of motion that has that form. So it's also an AR1. We sort of make the standard timing assumption that YT is not contemporaneously observable. So the agents are going to extrapolate out their forecasting model 2 periods. And so their expectation just depends on YT minus 1. So given those beliefs, that leads to an actual law of motion that also is an AR1. The AR1 root depends on those beliefs. And then the algorithm needs to update A in some way. And so here this is just the typical constant gain updating equations. So gamma is the gain. Okay. So the problem is, well, what if that root in the actual law of motion is bigger than 1 in absolute value? Then there's this possibility of having these explosive dynamics. And so we'd like to know how likely is it that you hit that region. So we just kind of parameterize the model in such a way that the MSV root, which is what the red dashed line is awfully close to 1. So the explosive beta A squared plus delta in this parameterization is about 1.03. And so then this is the histogram of the learning coefficient, the AR1 learning coefficient from Monte Carlo simulations of the model. And the blue dashed line is just the mean of that distribution. And so what you see is that there's a non-trivial fraction of the realizations that sort of enter into that region that might lead to instability. So, yeah.
If you go back to the original difference equation.
The expectation or this one?
Yeah, the expectation. It's got 2 roots, right?
Yes.
Yes. But one is stable. I think one's unstable. So we're right. So why are we focusing on the stable one? Yeah, I mean, so the stable one would be E stable and stable under learning, and the explosive one wouldn't.
Is the unstable one have any, is it informative at all about that histogram?
Oh, whether it's being drawn to that? You know, I don't know. It's a good question. I've wondered about this before, and so without the, okay, so let's imagine that delta is 0. So if we look at, so in there, right, okay, so then we don't have the 2 roots, but what you do have is you have this, right, yeah, you do have 2, right. And so if you look at, say, the mean dynamics, the mean dynamic equation for the constant gain learning in that, you see, depending on some initial conditions, that you get drawn towards that other root temporarily, but don't ever quite hit it. So I've wondered about that also, whether the extent to which that unstable root is drawing you in some way.
And is the unstable root explosive too?
Yeah, the unstable root's explosive. Yeah.
Can you go back to the histogram?
The histogram, yes.
So this is whether or not a particular simulation reached the explosive region. Do you know how
Well, this is the whole distribution of the realizations of the coefficient. But this would be, you would enter, I have quotes here on explosive, by the way. If you went beyond about that point, these realizations past that would be the entering into the explosive region.
The histogram of the time?
Of the state variable.
No, the hitting time. How?
Oh, yeah, no, I didn't do that. Motivating example. Okay, so we've done this with other applications.
So this is a histogram, I don't understand it, with a projection facility, or does it even exist without a projection facility, or does it depend on the projection facility?
Right, there's a projection facility here.
Okay.
And then, yeah, whether you, I mean, you, having a histogram like that, right, if you're encountering the explosive dynamics, I don't know. So, I mean, we sort of pick our coefficients carefully to sidestep what you're worried about.
But you just can't draw that thing without
Right.
making an assumption about projection facility, because I suppose without it, it wouldn't exist. No, it would be
Right,
somewhere.
right. Okay. Okay, so what do people do when we're worried about this? So it seems, I mean, one strong motivation, it seems to be, in picking the gain sizes, is to restrict it in a way so that you don't really worry that much about hitting that projection facility. Then, of course, there's just the choice of the projection facility, what I call the art to the student. You know, in some cases, people will throw out paths. So you do some kind of empirical Monte Carlo exercise, and then, you know, not every simulation is exploding. We'll just get rid of the ones that do. Okay, so that works. And then, well, maybe if there's just some troublesome coefficients, you give the agents full information about those and not worry about it. Okay, so I think it's not just a computational issue. In applied studies that are making use of constant gain learning, you need to wonder a little bit about the role of the projection facility. And so I don't think it's just that, you know, there's too much instability. Maybe that there's too little instability. I don't know. Okay, so then as Kars discussed in the first talk, there's a way out of it. If you don't want the explosiveness and you don't want the projection facility, the sample autocorrelation coefficient learning gives that to you. And so here you can have the agents estimate AR1 and then just use the sample mean and autocorrelation coefficients to come up with the coefficient estimates for the AR1. And then these are, of course, naturally bounded between -1 and 1. And then I won't review what Kars already discussed this morning. So we're interested, right? So I said I'm picking on constant gain learning. So we want a constant gain version of that sample autocorrelation learning. We're going to call it YW learning. I'll tell you what that is later. And so this is what we think our specification of the constant gain looks like. So we're just taking the sample moments, but there are these geometrically weighted averages with this gain value gamma. And then we just need an adjustment term on there. An adjustment, you just kind of think of it like a degree of freedom adjustment. And so that's what it looks like. So it looks just like what Kars had, except for these weights that are in there. Okay, and so then there's the same histogram. So the first thing I want to say is you see some realizations of that coefficient that look like it's bigger than 1. That's just a figment of the funny kernel density estimator. There are actually no realizations that are above 1, because it can't. And so here now you see that this is better behaved in one sense, which that you're not worrying about the projection facility. There's a bit more bias in the estimator than there was in the constant gain. Okay, so in the paper, what we do is we're generalizing that sample autocorrelation coefficient learning to multivariate settings.
So like I have a Bayesian interpretation where the guy's doing, except he has a prior that's
Right, so I would think this would be the sort of classical answer to putting a prior that rules out explosive
or is there some
non-stationary
prior that you
processes.
guys are gonna have or something?
No.
Can I follow up on that? Suppose your prior was truncated on 0.9999, and if you get any estimate out of greater than, you
Just throw it out. I mean, I think that's the interpretation of the projection facility.
this threshold kind of a projection facility as different from the one you are suggesting. You know, like how it affects the limiting, where do we go, how the distribution looks like.
So, I guess I don't know the answer to that. I mean, so the limiting distribution is typically computed under assumption of sort of vanishing gains. And so then you're not, I'm not sure. It's a good question. I don't know the answer to it.
So it might be quite similar. OLS with the projection facility -1 plus 1 might be very similar to simple automation.
You mean the asymptotic distribution?
I doubt it.
No,
I doubt it too,
think
but
you
I don't
get
know.
piling up on the boundary under least squares learning with a projection facility. You don't get that with this. We could look.
Okay, so the generalization is, so this is the YW. So it's based on the Yulee-Walker estimation of VARs. So Yulee-Walker equations are a way of identifying the coefficients of the VARs using sample moments. And so we have a theorem that says, just like in the univariate case, that the sample autocorrelation coefficients are between -1 and 1, we have that the coefficients remain bounded as well in a sort of multivariate sense. And then we have applications which show, okay, well, the constant gain Yulee-Walker learning is stable in cases where you would need the projection facility with constant gain least squares.
So by bounded, you mean they imply non-explosive dynamics, or what does bounded mean?
Let's just, I'll tell you what I mean when we get there. It's like one slide away. Yule. Okay, Yule. I'm going to keep saying Yulee. I'm sorry.
Tom says it's Yule.
Yule or Yule?
Except
Yule.
you're the first guys I've ever heard not say Yule Walker.
Welcome to Oregon.
It's a- yeah, or welcome to a learning center.
Right.
Like why do
Okay. So here's how it would work. So what the agents want to do is estimate a VAR of R1, and so right, this is very flexible because you can always stack things into a VAR1 form. The Yulee-Walker equations, this is gonna get, the YW equations, in terms of the population moments, would look like this. And so the idea of the learning is just to replace the A and C in real time using their sample counterparts. Okay, so it seemed to us when we first thought about it that it must be obvious that the bounds of the sample autocorrelation coefficients must be true in the multivariate sense as well. And so looking in obvious places, it didn't seem that we could find a proof of that. And so then Bruce wrote one down, and this is the theorem. And so this is the bounded in the sense that the roots of that autocorrelation coefficient, matrix A, are bounded with eigenvalues inside the unit circle. So that doesn't mean that the actual law of motion in a self-referential system is always going to be stable. That's clearly not true. It just means that those roots are always going to be inside the unit circle, even if you're on an explosive path.
And that's a strange estimator.
Then that would be a right. So that would be an estimator that you might not
In those cases.
move your priors.
Not necessarily, if you're Bayesian.
Yeah, if you believe in your prior, that's it.
Yeah. You're patient.
It's like him, I can say Yule all day.
Yeah. Dog, man. Yulee-Walker.
So the development of the constant gain YW learning model. Okay, so we start with a weighted estimator. That's the way we always think about the constant gain anyway, is that these are geometrically declining weights on data. So a weighted estimator would just look like this. So you have different weights, and then that's what the YW estimator would look like. And so then the theorem would apply to this as well, because what is this? This is just a YW estimator of the weighted data. Okay, so then coming up with the constant gain version, it's just a matter of choosing the weights in the right way. And so this is what it looks like. So the one trick about this is that if you have a non-zero mean that you're estimating as well, at the development of the estimator, you have to demean the data at each point in time. And so it makes coming up with a recursive version of this challenging. So there's an estimate at any time t of the sample mean. Given that, one can demean the whole data vector, and then on that demean data vector, compute the variance and the autocovariance matrices, and then estimate rules like that. And so it's just like that weighted YW estimator, choosing the weights in the right way. And so the thing all goes back to you're summing over the numerator and the denominator in different ways. And so because of that, you end up kind of with this adjustment term that's out there. Okay, how much time do I have?
You're doing great.
Depends.
You have 15 minutes.
15 minutes, okay. Okay, good. No, I guess I said it. So coming up with a recursive version of it's kind of challenging. So you can think of a way of doing it, just sort of call it a double recursion, which is so you recursively update your mean, and you transform the data, and then you can just kind of iterate on those equations. And boy, did that. So that's kind of nice because it looks like what the constant gain learning equations, recursions look like. But boy, is it a mistake if you want to do it in practice. It sure is slow. So you're just sort of doing this double loop as you go along. That's a big mistake. So that kind of double recursion is very slow. We have another version of it in the paper where we have the recursions just in the sample moments, and then we just have a terribly messy expression for the estimator. So one could do that, and then just the fastest thing is just to do the sums. Okay, so the open question, this is what we are struggling with a bit, is the convergence analysis. So so far we're challenged in putting the estimator into the sort of standard formulation of the stochastic recursive algorithm. And so our intuition is that all of the sort of standard results are going to apply here, but that's still an open question that we have. Okay, so the first application is a hybrid New Keynesian model. So this application is, let's pick a model where people run into problems, needing projection facilities, and make the model so that the problems are terrible.
This intriguing thing about where the stumbling block is. Do you want to say more about that? Just even.
In the on the previous slide, what he was just talking about,
Yes.
the stumbling block involves the initial condition sits in your recursion, and the stochastic recursive algorithm theory doesn't allow for accommodating that initial condition in an easy manner. I think the theorems of Young can be modified relatively easily to account for it.
Okay, so this is a version of the model that's going to lead to the most severe problems with the projection facility. So there's an IS equation that depends on lagged output, and then there's also lagged inflation in the Phillips curve. And then we want to get as much inertia into this model as possible, and so the policy rule also responds to lagged values. Okay. So this is nice. You can stack the equations, and so that the MSV solution to this is also going to be a var1. So then it's natural for the agents to form their expectations by estimating a var1 on these the stacked vector y, and then we could compare constant gain learning to Yulee-Walker, and then we're going to employ a projection facility when we do constant gain learning. So the projection facility is going to do two things. So one is it's just going to, when the coefficients of the AR coefficient matrix in the perceived law of motion are outside the unit circle, we're going to stop updating. And then we're also going to put bounds on x and pi, and these are all motivated by the Orphides and Williams papers. This isn't the model they use. So these are the histograms from the Monte Carlo simulations. The top row, those are the own AR coefficients, in the estimated model of the agent. So the A11 is the estimated error 1 coefficient for the output gap equation. A22 is for the inflation equation. The next row is giving the histogram of the outcomes. Output gap is X, and inflation's on the right. And so you can guess where the bounds are. They're at 50 and at 220, I think, or something like that. And so the projection facility has, okay, so the largest root of that A matrix can't be bigger than 1. And so you see that there's grouping, bunching, I guess, right there of the projection facility, and a lot of outcomes there. And then, so there was a question earlier about, no, I guess it was the first time I don't remember it, but we did look at, before the first time to hitting the projection facility, the bottom row is giving the fraction of the time in a simulation spent at the projection facility. And so it's non-trivial, it's bimodal. And so this is a gain, and this gain is 0.03.
Wait a second. Right, so I can integrate. I see. Got it.
And so 0.03 is what many people would choose or say is a reasonable value. Okay, so there's YW learning. So same gain, same thing as before, but now you see that we don't have that bimodal feature to it. We're not hitting the bounds. Things just look better than when they did before. The vertical line, why they're there, not the other one. I'm not sure. So those are the means of that of those distributions. Okay. Nobody ever does a gain of 0.15. With YW learning, you could, and you get more volatility, of course, but you're not running into this bounds issue.
You mentioned that this is better than the previous one. In what sense?
Well, I mean, okay, so to me, it depends on what your loss function is. Mine is not hitting the projection facility. And so, it depends. So here what's happening is there's in fact, a majority of the time, the simulations would explode. And none of them.
What about convergence rate as you drive the gain towards 0?
That's a good question. It's a good question. I'm not, it's slower, I think. So
slower?
I think YW learning is slower than constant gain. It's close.
But we haven't assessed that carefully.
We haven't assessed it carefully.
That's what we want to do, definitely.
Okay, so then the second application is related to the first presentation by Cars. So we're going to think about and generalize his 2004 JET paper. So this is what they did in 2004 JET. They had various models that all kind of fit this form. It was a linear univariate model that depended on forward expectations, and it depended on an exogenous serially correlated process. So that in MSV, YT is just proportional to that exogenous process. And so the question that they're interested in is, well, what if this VT process is never observable to the agents? And then YT is not contemporaneously observable. And the agents then are just going to fit ARP models. We were thinking ARP, they had AR1. So YW learning is a natural estimator for this because you could stack the ARP into a var1. So there was a question about by Jim about just adding more AR roots. So this slide is going to show you it's always going to be misspecified. So just take the simple case where the agents have AR1 beliefs. Okay, so then this is just like the motivating example. So the actual law of motion is also going to be this AR1 plus the serially correlated process. Well, you just do a little bit of algebra, and then you see that the actual law of motion actually is an AR2. And so the AR1 beliefs are going to pick up this extra root. And so then if they tried to fit an AR3, it'd be, or an AR2 would be an AR3. AR3 would be an AR4. And so they're necessarily going to be misspecified. So the learning process will never converge to the rational expectations equilibrium. The right equilibrium concept here to us is the restricted perceptions equilibrium, which is that the coefficients of that model should just be the best fitting model within this restricted class. Okay, so you can just see that sort of more generally. So but before they didn't have a constant, but now we just give them an AR1 with a constant, or ARP, and then natural law of motion is going to be an ARP plus 1. And so then the coefficient matrix then is going to satisfy this least squares orthogonality condition, which has a projection of yt onto this limited space of regressors. Okay, and so then solving that out for phi then gives the right notion of a T-map here, which is given these perceived coefficients, that leads to an actual process for yt, and then they can compute what their linear projection of yt onto that space is, and that's what T of phi gives us. And so an RPE is just a fixed point of that T-map. Okay, so there's a similar notion of E-stability. So with that T-map, then the E-stability ODE is just going to tell us the direction of adjustment for what phi should be, and it just says, well, you adjusted in the direction that you were off in your estimates. And so with E-stability, then we could identify the locally stable resting points. The connection to YW learning, as I said, we haven't made, but it's useful for thinking about Y projection facility. It's complicated even in this simple environment. So the example we're going to do is, so this is just extending what CARS did. So CARS had them fitting AR1. So here they're going to fit AR2. The shaded yellow triangle region is, so those are the sets of coefficients consistent with a stable process for YT. The other lines, the dashed red line and the black line, those are the contours associated to the fixed points of the T-map. So where those lines cross within the shaded region, that's an RPE. And then this is two cases. So the left is where the model is determinate, and on the right is a case of where the model is indeterminate. And in the right, there's a single unique RPE, and on the, did I get it wrong? Left, okay, left is unique. On the right, you can see that there's multiple, there's 3 RPE. The little blue dot is telling us that which equilibria are stable. And then if we just look at the vector field implied by the E-stability OD, and it sort of makes more clear where those blue dots come from. So there are lots of arrows pointing towards the blue dot. So I look at this and then I say, okay, you tell me where you would make the projection facility. You think, well, it's just in that shaded region, but there's places that shaded region that are going to bounce you out of that shaded region. So this is kind of the point of the art to it, I think, is that even in the simple model, it's not really clear how you want to do that.
But if you reach those points only with very low probability, it doesn't matter for the sample nodes that much.
No, that's right, with very low probability. I mean, I guess to me, it's like
for the outcomes of the predicted outcomes of the model.
Right, but if you're doing an applied study and you're choosing or calibrating or estimating your coefficients, and part of that estimation, calibration, choice procedure is trying to keep you away from that projection facility, then that matters in some way. Why? So why do we have gains of 0.01 instead of 0.15?
Because we want to stay away from the projection.
Right?
Is that right?
I don't know.
I thought because we want to match some survey data.
Right, but maybe I guess what I'm saying is it's not clear whether you're getting the best fit when you're subjecting yourself to this constraint of the projection facility. And if you didn't have that, maybe the fit of your model would be better, maybe the size of your gains would be better, maybe people wouldn't shout and yell if you had a gain of 0.15 instead of 0.02. So then this is okay. So if I do the constant gain learning again, looking at the histograms, you see that there's a lot of hitting those projection facilities. With you could do different projection facilities. So in this one, we're just sort of we're shrinking the estimates back into the stability region. If you bounce into it, you could change the rates at which you're doing it. So shrinking faster. You could also kind of repeatedly shrink to make sure that you're in the stable region. And you can see that the mean time that you're at a projection facility depends a lot on what the details are of your projection facility. Okay, but with the YW learning, it's not an issue. I interpret that as my time's up. Okay, so if one is doing constant gain learning and one is worried about the projection facility or would like to dispense with it, the YW learning is a nice way to